Good afternoon, everybody. Um, I'm Fahed Salahat from Kansas State University. I will be talking today about rigorous yield line analysis to evaluate the capacity of reinforced concrete barriers subjected to vehicular collision load. This work was supervised by Professor Haider Rashid and Professor Christopher Jones and funded by Kansas Department of Transportation. So in today's presentation, my outline is to introduce the topic and talk about the background of the research and our contribution. Then we will give a short introduction about the yield line analysis, reflect AASHTO's procedure for the yield line analysis, and then our rigorous and detailed procedure. We will consider a case study to compare both, and then we conclude with some recommendations. So collision events happen usually with the piers, vehicular collisions. And so because of this, AASHTO considered the vehicular collision force as a design limit state. To address this limit state, you can either provide the bridge pier with a resistance to an equivalent static force of 2,670 kilonewton, or provide an intervening structure that can absorb or redirect the colliding vehicle. And this intervening structure should survive test level 5 according to the MASH, which is the Manual for Assessing Safety Hardware. Reinforced concrete barriers are very common structures used as intervening structures. And the framework to place them for this purpose include selecting the test level that they are supposed to survive, and then doing the analysis and design for these barriers. Finally, consider them for experimental testing or numerical simulation. Our contribution comes in actually the second one, which is this one, where we want to see what are the available methodologies for the analysis and how can we modify them or enhance them. So we want to develop rigorous analysis and detailed one to accurately evaluate the transverse capacity of reinforced concrete barriers to withstand vehicular collision forces. The methodology that was followed to achieve this purpose is by first exploring the available and the currently existing methodologies, and namely the one that AASHTO adopts, which is the yield line analysis, and then work on this methodology to highlight the disadvantages and underestimation factors and work on detailed analysis to overcome these, verify the proposed and the detailed analysis by finite element modeling. So what is yield line analysis? It is the most common methodology to obtain the transverse capacity of reinforced concrete barriers. And it's basically based on equating the internal energy stored in the barrier with the external work applied by the applied forces to find the critical failure load according to a failure pattern. This failure pattern is important in determining the maximum or the capacity, the lateral capacity of the barrier. AASHTO adopts the V-shaped failure pattern, which actually induces two yield lines in the front face of the barrier and one at the back. And many researchers actually criticized this failure pattern. For instance, Cao et al. In 2020, they suggested W-shaped failure pattern. And our hypothesis is that the V-shaped failure pattern can accurately predict the lateral capacity of reinforced concrete barriers if the assumptions that AASHTO introduced to simplify the analysis process can be, some of them can be avoided. And these assumptions are 5. If one can refer to AASHTO's chapter 13, they are stated there. The first two assumptions are reasonably acceptable, which are that the slab deck has enough strength to resist the lateral load, so the failure will happen in the parapet. And the other one is that the barrier has sufficient length so that the yield lines will develop in the parapet. However, the last 3 ones are the underestimating ones, which are the flexural capacity of reinforced concrete barriers is from the concrete contribution. No contribution is coming from the steel, and this is obviously underestimating one. And if the wall has different widths in the section, we can average the width so that the average width will represent the sectional width. And this, as you can see, averaging the width will reduce the width at the bottom where the moment is higher due to the cantilever action, and reduces the moment capacity at that location where it's needed, and add these moment capacities where they are not needed. And finally, it's assumed that the negative and the positive moments or sectional capacity are equal, which in this case you can see that we have less reinforcement at the back side of the barrier than the front face, and that will, if we are to consider them equal, then we have to go with the less or the lower one, and that's also underestimation factor. So according to the current process of AASHTO, equation 1 and 2 will give us the lateral or the wall resistance. We first go to table A13.2-1 to obtain for a certain barrier. We obtain the distance LT, which is the distance that the load is applied along. Then we plug LT in equation 2, and then from equation 2 back to equation 1 to obtain the wall resistance. Our contribution comes here to overcome those three underestimating factors. And we made two assumptions. The first one is that the concrete is inextensible through the thickness. And the second one, we want to measure the rotations of the sections with respect to a vertical plan. So the inclined surfaces that have an actual rotations of theta 2 and theta 3, we will consider those as theta 1 in our calculations to simplify the analysis process. However, we derived theta 1, theta 2, and theta 3 mathematically due to one unit deformation at the top, and the differences are very minor, so we were happy with this assumption. As you can see, the differences between equation 3 and equation 4 and 5 are minor due to the difference in the numerator. So the process includes obtaining detailed sectional capacity, and here is an outline how to do that. However, I'm going to skip that and go in details when we consider the case study and take them step by step. And also, according to our failure pattern, it's, as we mentioned previously, it's a V-shaped. So we have two yield lines at the front face, and then we have a vertical yield line at the back side. We want to do an integration of the sectional capacity along the height of the barrier. So we need everything, all the rotations, all the moment as a function of the depth, Z. And Z is measured from the top of the barrier all the way to the bottom. And we can see here how we derive these from trigonometric relationships, and the formulation of all these quantities are shown. Then the internal energy is given by equation 18, the final internal energy. And we need also, in order to solve this problem, we need the external work. And the external work due to distributed load to represent the vehicular collision can be found as the distributed load times the area of the deformed shape, as you can see here, which is equation 21. If we equate both sides of the internal and the external work, then we can obtain a final and closed form solution for the lateral distributed load that represents the lateral capacity of the barrier. Deriving this equation, equation 22, with respect to the angle of orientation of the yield line, will give us the minimum load WT. We can also plot the function with respect to a various angles, range of angles, and then we pick the minimum value of that plot, as we can see in the next slides. So here comes the case study. First, this is a barrier, very common barrier that was the drawings were provided by Kansas Department of Transportation. The reinforcement and the concrete properties and steel, as here shown. We start by AASHTO's yield line analysis, applying all the simplifying assumptions and the process. Because of the fact that AASHTO's equations are in US units, this is the equivalent barrier in US units. And if we eliminate the steel reinforcement as per assumption 1. Everything is based on the modulus of rupture of the concrete. Then we can go to calculate the sectional capacity as shown in this table. And we go to table A13.2-1 to find LT, plug it in equation 1, then in equation 2, then back to equation 1. The wall resistance will be 56.2 kilopounds, which is equivalent to 250 kilonewton. It's worth mentioning that this barrier was, according to the AASHTO, should resist a minimum force of 54 kilopounds. So it's obviously it's designed for that purpose. And this is 25 kilonewtons of resistance. Now, is that the actual resistance of the barrier? We can see now by our detailed and rigorous analysis. We need, in order to obtain the sectional capacities around the horizontal and vertical axes, we need detailed layout of the rebar so that we can obtain an integration along the height or along the height of the section. And now we start with the back side, and along the vertical axis, we can see that the barrier has two different sections at the bottom and the top. So there's a point of discontinuity here. So this is one section, and this is the other section along the vertical axis. So if we start with this one, section 1, we find all the reinforcement at the backside divided by the height of the section to find distribution of the area of steel. Then we find a weighted average for the cover. And then we find the function of the moment with respect to the weighted average and along the Z. Doing this for section 2, we will end up with a moment equation that covers the two sections. The same exact process for the front side, because the area of steel is going to be different, but the process is the same. And the distance between the centroid of the rebar and the front face will be different from that of the back, according to the cover. So we will have another moment function. For the moment along the about the longitudinal axis, we will have three sections of the continuity. One at the very top of the section that at the very top of the barrier, then at the point of discontinuity, and then at the bottom of the barrier. For one for 1 feet length segment, we can obtain these quantities of the moment and connect them with a linear variation function to obtain the moment function as a function of the depth Z. The same for the front side. And then we will end up with all the moment functions along the vertical and horizontal axes as function of the depth Z. We plug them into equation 22 to obtain equation 29. The same length LT, which is as per AASHTO, to apply the lateral force. Then we will obtain equation 30 by the closed form. Plotting this equation for a various and wide range of angles covering between 0 and 70 degrees, we can see that the critical point gives a force of about 570 kilonewton, and the angle of orientation for the angle of inclination for the yield lines is 30 degrees. To verify our solution, we went to finite element analysis by Abacus, and the model contained the steel and the concrete. The concrete was modeled by the concrete damage plasticity, and the steel was a bilinear material model. The concrete elements were 8-node linear brick elements, and the steel were modeled as beam elements. The constitutive relations of the material for the concrete and the steel is shown here. The mesh was 60 millimeter by 60 millimeter by 40 for the concrete solid elements, and we had the load applied at the loading surface, as you can see here, the loading surface, which is this distance. This distance is LT, and this is the depth of the first segment, which is 560 millimeters. So this loading area, if we have this loading area, and apply a pressure of 1.72 megapascal at this, the ultimate load or the target pressure will give us the peak load, will give us 1,027 kilonewton. However, we analyzed the structure using RIX analysis, and RIX analysis gives you the failure as a load proportionality factor. So if the structure survived this much force, the load proportionality factor is going to be 1. But our case, the load proportionality factor was 0.55 times this, the target force yielded 554 kilonewton. You can see here that the strain in the steel elements, as shown here in this, if we track the points, the steel elements that has the maximum strain values, we can draw a line that represents the yield line in the steel reinforcement. With this height of the barrier and this width, we can obtain an angle alpha of 30. And you can see here the deformation and the plastic, the absolute principal strain in the concrete can be shown to draw, also represent the yield lines formation, which is pretty much the V shape we talked about. And finally, to summarize and compare all the results, we can see a normalized value for AASHTO, which is 1 to 250 kilonewton. The rigorous yield line analysis is 2.276, and a very close agreement and perfect agreement actually with the finite element model. And our conclusion is that the currently adopted AASHTO procedure for obtaining the capacity of reinforced concrete barrier underestimates the actual capacity by 50%. So our suggested and proposed detailed yield line analysis is very powerful in obtaining the accurate capacity, and it's also not very complicated to apply. If one understands the process, it's easy to apply and implement. And it's important to highlight that if we are to use AASHTO's yield line procedure for initially proportioning, so that the barrier is then going to be to undergo experimental testing and further layers of design and optimization, that's fine. But if we are to actually judge or want to have a feeling about existing barriers, how much the lateral capacity of these barriers, and using the AASHTO's procedures, this is going to be underestimating by much. And then at that point, we will need exact and closed form solutions, either by finite element analysis or by this proposed yield line analysis to obtain the actual capacity. With this, I would like to thank you, and I am very happy to have any questions that you may have.